Hello everyone, I am Vanilla Priya.
And I'm Shruti. We are excited to share our presentation on divide and conquer paradigm. Here is the outline of today's presentation. We'll be exploring this concept through two key sorting algorithms, merge sort and Bitonic sort, to show how divide and conquer helps solve problems efficiently. So, let's dive right in and see how this algorithm technique works. So, let me start by talking about divide and conquer paradigm, which is a very common and powerful technique in computer science. The idea is pretty simple. When you have a complex problem, instead of solving it all at once, you break it down into smaller, easier to solve subproblems. Once you have these smaller pieces, you solve each one independently. After that, you take all these solutions and combine them to get the solution to the original problem. So, it's really about breaking things down, solving the pieces, and then putting them back together. This approach is especially useful in sorting algorithms called merge sort and Botanic sort, which we are going to look at today. Both of these algorithms use divide and conquer to achieve better efficiency, especially for larger datasets. Now, Vanilla will explain the merge sort algorithm.
Now let's talk about merge sort, which is one of the best examples of the divide and conquer approach. So how does it work? Well, it starts by dividing the array into two halves. This process continues recursively until each part contains just a single element. Now at this point, each element is trivially sorted because there is only one item. Then the second step is to conquer, meaning we recursively sort each half of the array. Once all the subarrays are sorted, we move to the final step, which is combining. Here, the smaller sorted arrays are merged back together, but in the correct order to form a fully sorted array. One of the key things to know about merge sort is its time complexity, which is O of n log n, in the best, average, and worst cases. The reason for this is that we are doing log n levels of division, and at each level, the merging process takes linear time or O of n. Merge sort is also stable, meaning it preserves the order of equal elements, which can be important in certain applications. However, it's not an in-place algorithm because it requires extra memory for merging process. Overall, merge sort is a very efficient algorithm, especially for larger data sets, thanks to its predictable time complexity. Now let's have a glance over algorithm of merge sort. The pseudocode for merge sort starts by recursively dividing the array into two halves until each subarray contains a single element. Then it merges the two sorted halves by comparing elements from both halves and placing the smaller one into the original array. This merging process continues until the entire array is sorted. The key steps are dividing the array, sorting each half, and merging them back together. Alright, let's walk through how merge sort works step by step on the array 12, 8, 9, 3, 11, 5, and 4. The first thing merge sort does is split the array into two halves. So we start by dividing 12, 8, 9, 3, 11, 5, and 4 two halves, that is 12, 8, and 9, and 3, 11, 5, and 4. But we are not done dividing it. We'll still keep splitting each half until we get subarrays that contain just one element each. So now let's have a look at the first left half, and that is 12, 8, and 9. We now divide it into 12 and 8, 9. And now we'll go take a look at right half, that is 3, 11, 5, and 4. We'll divide that into 3, 11, and 5, and 4. Now we're not done yet. So now we'll divide 8, 9 to 8 and 9, and 3, 11 to 3 and 11, and 5 and 4 to 5 and 4. So now let's start merging as we have all single elements. So let's start merging, and we have 8 and 9 combined together, and they are in sorted order, that is ascending order. Now we'll combine 3 and 11, and they're also in sorted order, that is ascending order. And now we'll combine 5 and 4, but here 5 is greater than 4. So we'll just swap 5 to the right side and we'll place 4 in the left side. So now they're also sorted. Now let's go into the next step of merging. So now we'll combine 12, 8, and 9, but they're not in descending order. So now let's bring 8 and 9 to the left and 12 goes to the right. Here, 3 and 11, 3 is the smaller one, but 11 is the bigger of 4 and 5. So we'll keep into the right. And 4 and 5 are in sorted order. So we'll just place it here. Now there is just one more step of merging. So here we'll merge 8, 9, 11, 12. But here 11 comes in the middle because 11 is less than 12. But 3, 4, 5 are in sorted order. So we got the final sorted array. As you can see, merge sort works by continually splitting the array into smaller subarrays and then merging them back together in sorted order. This is where the merging this is where the divide and conquer paradigm really shines because we are breaking down the problem and then efficiently combining the results. And that's how merge sort works. Now that we have seen how merge sort uses divide and conquer, let's move on into another interesting algorithm, Bytonic sort. Bytonic sort is especially useful when parallel computing and works by creating Bytonic sequences. To explain this in more detail, I'll hand it over to you, Shruti.
Thank you, Vanilla. Now I'll walk you through an exciting parallel sorting algorithm called Bytonic sort. Bytonic sort is a parallel sorting algorithm basically built on something called Bytonic sequence. A Bytonic sequence is a sequence that first increases and then decreases, or vice versa. The core idea here is to break the array into smaller subsequences repeatedly. One half of the array is sorted in ascending order and the other half in descending order. Finally, Bytonic sort uses a merge function to combine these sorted halves. This merge process aligns the elements in the particular direction, either fully ascending or descending, until the entire array is sorted. Now, let's take a closer look at how the algorithm works step by step. The Bytonic sort function takes two inputs. First is the array to be sorted, and secondly, the direction in which we want the final result, either ascending or descending. Here is how it works. First, it checks if the length of the array is greater than 1. If it is, the array is split into two halves. The first half is sorted in ascending order, and the second half is sorted in descending order. After sorting both halves, the merge function combines them in final specified direction. Now let's break down the merge function used in the Bytonic sort. The purpose of this function is to compare elements from two halves of the array and swap them if necessary based on the specified direction. We are sorting in ascending order. Larger elements are swapped to the right, and the same logic applies in reverse for descending order. The point to be noted here is Bytonic merge algorithm compares elements across the two halves, not adjacent, but elements with a gap of n by 2 indices. As you can see here, we are comparing ith element with I plus n by 2th element and swapping them based on the specified direction in merge function. While merge sort directly compares adjacent elements from the two halves in sequential order. Let's take a closer look by taking an array example. In Bytonic sort, the first step is to break this array into two halves. Here, the left half is eventually sorted in ascending order and the right half in descending order. But we do not sort them right away. Instead, we recursively split the array further into smaller subsequences. Now we begin breaking down the array further into smaller subsequences until the array length becomes equals to 1. Now at the final step, we have a smaller subsequences of length 1 which are ready for the merge step. Here we begin the process of merging using Bytonic merge function according to the direction mentioned. 2, 19, 1857 are merged in ascending order, while 72, 3, 86, 80 are merged in descending order. And the same merging process continues until we get one subarray in ascending order and another in descending order, resulting in a Bytonic sequence. So here is our final Bytonic sequence where the first half of the elements are in ascending order and the second half of the elements are in descending order. Now we move on to the final merging step where this Bytonic sequence will be converted into one fully sorted array. Here is how the final merge works. We compare and swap elements with an index difference of n by 2, which is equals to 4. So we'll be comparing 2 with 86, 3 with 80, and so on. And in the next step, as n reduced to half, we will be comparing elements with an index gap of 2. So 2 is compared with 19, 3 is compared with 18, 86 with 57, and 80 with 72. And in the final step, we will be comparing elements which are adjacent to each other like 2, 3, 19, 18, 57, 72, and 86, 80. And here is how we obtain the final sorted array in the Bytonic sorting. To recap, Bytonic sort first breaks the array into smaller subsequences, recursively sorting them into Bytonic sequences, one half in ascending order and the other half in descending order. The final merge process ensures that all the elements are compared and swapped to create a fully sorted array. What makes this algorithm particularly powerful is the ability to handle larger data sets efficiently, making it ideal for parallel processing environments. Now, Venla will take over and explain the real world applications of divide and conquer paradigm.
Let's take a closer look at the real world applications of divide and conquer. This approach is widely used across various fields, particularly in sorting algorithms like merge sort and quicksort. These algorithms are essential for organizing data effectively in databases and file systems. Additionally, divide and conquer plays a critical role in binary search, which enables efficient retrieval of data from sorted data sets. It is also utilized in geometric algorithms where it addresses complex problems in computational geometry. Another notable application is in advanced matrix multiplication, such as Strachan's algorithm, which enhances performance when handling large matrices. Moving on to divide and conquer in parallel computing, this paradigm is particularly well suited for such algorithms because it allows independence of problems to be solved simultaneously on multiple processes. This capability significantly improves execution speed, especially in modern systems like GPUs and cloud computing. To help visualize this process, we can use techniques like recursive trees and flow diagrams. These visualization methods effectively illustrate how the divide and conquer approach systematically breaks down complex problems and combines solutions, making the overall process clearer and more intuitive. In conclusion, divide and conquer paradigm stands as a cornerstone in the realm of algorithm and design. In conclusion, the divide and conquer paradigm stands as a cornerstone in the realm of algorithm design and computational problem solving. By effectively breaking down complex problems into smaller, more manageable subproblems, it not only enhances time complexity but also capitalizes on the power of parallel processing in today's advanced computing environments. From its vital applications in sorting and searching to its impact on geometric algorithms and matrix multiplication, divide and conquer has proven to be a versatile and indispensable approach in various fields. As we continue to push the boundaries of technology, mastering and applying this paradigm will be essential in addressing the increasingly intricate challenges we face in computer science and beyond. Thank you all for your attention.